Good morning, everyone. Today we will continue our topic, RC circuits. We're going to go through again the cases for the capacitor when the capacitor is being switched in or switched out in the circuit, and what happens after right after switching moment and later on when the capacitor is being switched in for a long time or switched out for a long time. So let's look at those cases. So let's assume we have a circuit that this circuit is made of a resistor and here a capacitor. Again, I have a switch here and a battery. So this is switch is switched on at t equals to 0. So once I close the switch right at the moment of t equals 0, the capacitor will be, if the capacitor is fully discharged, no charges in this capacitor, the capacitor will be replaced at t equals 0, will be replaced by a piece of wire. So I will redraw the circuit again. So I have here R1. This is the capacitor here. The switch now is closed. Right? R1, R2, R3, and right at the t equals 0, only this moment, the capacitor here will be replaced by a wire, a piece of wire. So what's going to happen to the circuit? Right at the t equals 0, all the current is going to go and this branch and nothing is going to go here. Right at the t equals 0, only at t equals 0. Then what's going to happen? The capacitor will start building charges, and now this current here that's going through the capacitor will start to decrease, and this current that's going through the two resistors will start to increase. So again, this is the case for a capacitor being charged. So if I look at this current here, the current would look like, so this is the current I, and this is the time. So the current is starting here from maximum, which is right at this moment of the t equals 0. I have maximum current, and then this is here IC, and then the current start to decrease till it reaches 0. It will reach 0 right at the infinite time, which is now the switch is closed for a long time. So what's going to happen? Here is the case where the switch is closed for a long time. Here at the t equals to 0 is the switch that is closed at t equals 0. So notice what's going to happen here when the switch is closed at long time. When the switch is closed now at long time, the capacitor would be now completely charged. No more current is going to go through the capacitor, and now the capacitor can be treated as an open circuit. So here, if I am to call this one at t infinity, which is after the switch is being closed, long time after the switch is being closed. Now my circuit is going to look like this. My, my capacitor now can be replaced by an open circuit. So the capacitor is being replaced here by an open circuit. Why? Because the capacitor is not being charged anymore. It reached its maximum. And what is this voltage drop across the capacitor? Let's look at the circuit and find out what components are in parallel with my capacitor. Then I can calculate the voltage drop across this capacitor when the switch is being closed for a long time. So in this case, I can see that the voltage drop across my capacitor here is the voltage drop across those two resistors that are in series, right? Those two resistors, the voltage drop across the equivalent resistance of those two resistors is the same voltage drop across my capacitor. So if I want to calculate the voltage drop across the capacitor when the switch has been closed for a long time, then I need to find the voltage drop across R2 and R3, which basically means here now I have no current going into this capacitor anymore. I is 0. The capacitor is fully charged. Then the voltage drop would be here. I have now this I that is going through those three resistors. Now those three resistors, when the switch has been closed for a long time, would be in series. So in order to find, so at the beginning I need to find this I, which is Vs divided by R1 plus R2 plus R3. This is I. And then in order to find the voltage drop across R2 and R3, which is delta V, which is also the delta VC, then delta VC, which is across the capacitor, equals to this I just found times R equivalent, which is R equivalent is R2 plus R3. This is the voltage drop across the capacitor when the capacitor with the switch is being closed for a long time. Now let's assume that I have a second switch that was already here, that was already closed. Now I need to open this switch. So what's going to happen? Let's look at the circuit and see what is going to happen to my capacitor. Our redraw this is the switch R1, R2, and R3. We have here delta VC that we calculated earlier, this Vs, and now this is switch number 2. Now, switch number 2, again, I will now have a new timing. So the timing for this one at t equals 0, I will open this switch. at t equals 0, I will open this switch. What's going to happen to my capacitor? Now, when I open the switch right at the t equals 0, the capacitor would be replaced by a battery, right? Why? Because it does have a charges. It is not fully discharged. It is a charged. It has a charges in it, and there is a potential difference across this capacitor. So once I open the switch, right at the moment of opening the switch, the capacitor here, since it is a charged, will be replaced by a battery. So the circuit's going to look like this. Now the switch is open, and the voltage across is delta VC, whatever voltage I calculated. And this is only going to be for this moment. Now, since this switch is open, this whole left part of my circuit can be eliminated. It has no influence whatsoever on my circuit. So I will redraw again. So my circuit here would look like this. So this is the capacitor that has been replaced by a battery, delta VC, and this is R2, and this is R3. So now what's going to happen? The capacitor is going to act as a battery, and the value of this battery is delta VC, and this value is only for the moment of t equals 0. So if I am to calculate now the current going through, let me call this one I2, then, or maybe I small letter 2, then this I2 equals to delta VC divided by R2 plus R3. So here, this current would be the highest current, and then will start to decay again. So this I2 here, then the current will start to decay again till the charges are completely discharged in the circuit. So this moment, which is at infinity, is when the switch is open for long time. So now when the switch is open, t equals to infinity here, it means long time. We've seen it switch being closed for long time. It is after the action. Here, switch has been open and open for long time. The capacitor now is fully discharged, and it would look like an open circuit, as if the circuit now is open. So there are no charges, which means now the current, as we have seen here, became zero, right? No currents. Currents in this circuit is zero, which means that the voltages across R2 and R3 are also zero. So those are the cases for the capacitor when the capacitor is switching right at this moment, and when this capacitor has been staying for a long time. For both cases, either if it was charged or if it was discharged, this is what's going to happen to the capacitor. So have a look, read the summary here. This summarizes what we have just mentioned. And let's now move to the next question. In this question, we have the following. Consider the circuit below. Switch S is closed at t equals 0. So at t equals 0, switch is going to close. What is the voltage across the capacitor long time after the switch is closed? The word long time means at t equals to infinity. So let's close this switch. If this switch is closed, we need to look at the voltage of the capacitor long time after the switch is closed. Remember the word long time, I replace the capacitor with an open circuit. So my capacitor here, my circuit is going to look like this. So I can see that the voltage drop across the capacitor would be the same as the voltage drop across the 2 ohm resistor. So for me, I can calculate now the current I, and then after I find the current I can find the voltage drop across the 2 ohm, and this would be my voltage across the capacitor. So here I is 6 divided by 3, I equals to 2 ampere. Then delta VC is I times 2, which is the 2 ohm here. Delta VC equals 2 times 2, which is 4 volts. So the answer here is B. Now for this question, we need to calculate the time constant tau and the ratio of the charge at 10 seconds to the maximum charge Q max of the capacitor in percentage. Now the switch here has closed at t equals to 0, then the capacitor will start charging. So let's first draw the circuit. So I have here 1 mega ohm. Then I have the capacitor, 10 microfarads. Then I have the switch. And this is 6 volt. And now the switch is closing at t equals 0. Then the capacitor will start charging. So if the capacitor starts charging, then let me first calculate tau, which is RC. The resistance that the capacitor is seeing while being charged is R, 1 mega ohm. So I have tau here as 1 10 to the power 6 times capacitance 10 power minus 6, and tau is 10 seconds. So this is my tau. Now, since the capacitor now is being charged, I can use the function that describes the charge, max 1 minus e to the power minus t over tau. So at t equals to 10 seconds, I have a q max 1 minus e to the power minus, at t equals to 10 seconds divided by tau, which is also 10. So here I have q t for 10 seconds equals to q max times 1 minus, so this one is 0.37, so q 10 seconds is q max times 0.63. I need the ratio, which is q t divided by q max, and this is 0.63. In percentage, I can say that qt divided by q max is 63%. Now, if you want to calculate the q max is the maximum charge that the capacitor is going to reach. And this is going to happen at the long time after the switch is closed. So let's look at this also. Long time after the switch is closed, my circuit's going to look like this. I have this voltage source, 6 volt, 1 mega ohm. Switch is closed long time. The capacitor is an open circuit. Delta VC. If you now take KVL at L1, I have here 6 minus, now what's the current here? The current is, due to the open circuit, the current is 0. So minus 1 mega times I, which is 0, minus delta VC equals to 0, and here delta VC is 6 volt. So Q max is C times delta VC. Q max is 10 power minus 10 minus 6 times 6. Then Q max would be 60 microcoulomb, in case you wanted to calculate Q max. Now the last question here is, consider the following circuits. The batteries and capacitors are identical. And the switches have been closed for a long time. At t equals 0, both switches are opened. Which pair of resistors dissipates more total energy? So here the switches have been closed for a long time, so we did not start the question yet. So here I can say at t equals 0, both now are open. So this is going to be t equals 0. So it was closed for a long time, and now at t equals 0, both opened. Which pair of resistors dissipates more total energy? Is it A or B? So number one, when the switch was closed for a long time, let's calculate the energy stored in each capacitor. So here, let's start with circuit A. I have 1 ohm, 2 ohm. When the switch was already closed for a long time, I want to find how much the voltage, 6 volts. So here the capacitor would look like an open circuit. Well, the switch was already closed for a long time. I want to calculate delta VCA. So delta VCA here is going to be the voltage across the 2 ohm. Why is that? Well, take the KVL. Take the KVL knowing that the current here is 0, right? It's an open circuit now. So the current here is 0. So delta VC would be the same as the voltage across the 2 ohm. So what is the voltage across the 2 ohm? Delta VCA is 6 volts, right? So the energy here, half C V squared, which is 6 squared. Now let's look at circuit number B. Circuit B, we have 2 ohm, 4, and also the capacitor. And we'll be looking at the capacitor when the switch was closed for a long time. So in this case, I have here 6 volt. I have here 2 ohm, 4 ohms, and now I'm looking at delta VCB. Again, since the current here is 0, then the delta VCB will be the same across the 2 ohm, and the 2 ohm has the 6 volt in parallel with, so delta VCB is also 6 volt, and the energy here is half C V squared. So both of them, they have the same stored energy. Now the question is, once this switch is open, which pair of resistors is going to dissipate more total energy? So here, when the switch is open for A, this capacitor is going to be replaced by a voltage source, by a battery. So let me open the switches here and here. Then my circuit's going to look like this. 1 ohm, 2 ohm. Now the switch is open, the voltage source is out of the picture. This one is 4, 2. Voltage source here is delta VCB. Now both capacitors, they have the same stored energy, which means both of them are going to dissipate this energy, which means that the total energy dissipated in both circuits A and B are going to be equal. What is going to be different is the rate of dissipation. Why? Because the path here are that this capacitor is dissipating the energy, and for circuit B, it's happening through this resistance, which is R equals to 6 ohm. However, if you look at the resistance that this total energy is being dissipated through, this resistance is 3, 3 ohm. So at the end, both of them are going to dissipate the same total energy, but the rate of dissipation is different. The question here is asking about which pair of resistors dissipates more total energy. The answer to this is C. Both pairs of resistors dissipate the same amount of energy. The question is not asking about the rate of dissipation, it's asking about the total dissipation of energy. So in this case, the C is the correct answer to this question.